Dear IOI friends, my name is Tom Verhoef, and I will tell you about the Olympiad trap and an old trampoline. After a short introduction, I will explain how a trampoline can be used to turn tail recursive function definitions into a loop, and how continuation passing style can be used to turn general recursive definitions, including branching recursion, into tail recursive definitions. I got involved in programming contests in 1985 via the ACM International Collegiate Programming Contest and from 1994 in the IOI. According to the IOI regulations, as you know, the IOI is about caring for young talent in informatics. The IOI format is that of an algorithmic problem-solving competition for individuals. Since a few years, C++ is the only programming language allowed. This seems hard to change. The IOI is trapped in its current format. Informatics has evolved considerably since the first IOI in 1989, and it still evolves. I fear that the IOI may miss out on young talent in informatics because of its format. A possible way to counter this is by paying attention to other aspects of informatics, such as functional programming, which offers an intriguing paradigm for computation. I will walk you through some simple examples. Consider the problem of computing triangular numbers. Given natural number n, try n returns the sum of the numbers n down to 0. Here you see a recursive definition for try n. It has linear recursion. Try n uses n plus 1 levels on the stack. In Python, try 1000 aborts with a recursion error. The definition of try n can be made tail recursive by introducing an integer accumulation parameter ACK, such that this specification holds. It is now easy to derive this tail recursive definition for try ACK. Instead of doing the tail call and creating a new stack frame, you can update the parameters and loop back using a while statement. Now try loop 1000 works as expected, but this manual rewriting of code is error-prone. There is a more systematic way. Instead of doing the tail call, it can be made lazy by wrapping it inside an empty lambda, that is, by returning a function without arguments, which the client can call to resume the suspended tail call. Is try ACK lazy recursive? You might think so because its definition contains a call to try ACK lazy. But it is not because that tail call is suspended. It is treated as data. To make try ACK lazy compute triangular numbers, we can use a trampoline, which repeatedly resumes the suspended tail calls. Together with the generic trampoline, the stack is not loaded, and it can compute try 1000 without overflowing the stack. The recipe is simple. Insert an empty lambda before every tail call. The generic trampoline then turns lazy tail recursion into a loop. There is now only one loop, which can handle all lazy tail recursive functions. The trick with the accumulation parameter will not always work to get a tail recursive definition. In particular, it will not work in case of branching recursion. But continuation passing style, CPS, works quite generally. Here is the generalization of try with an accumulation parameter again. This can be further generalized by introducing a continuation parameter cont, which is a function to be applied to the result. It is now straightforward to calculate a tail recursive definition. The work that needs to be done after the recursive call can be composed into the continuation. Thus, we get a tail recursive definition where the continuation parameter accumulates all the after work. In the base case, the continuation is finally applied to the base value. Note that in the tail call, the continuation isn't called, but is treated as data. Using the earlier recipe, this definition can be made lazy. Note that there are 3 tail calls to be made lazy. And with the trampoline, we can again calculate try 1000 without hitting the stack limit. Let's now see how this works out with branching recursion. Let tree be a binary tree type with integer values in the leaves. Summing all values in such a tree is done by the recursive function total. It exhibits branching recursion. Stack usage goes up and down while the example tree is recursively processed. It is slightly harder to apply CPS and obtain a tail recursive definition total CPS. Note that the second call of total CPS with argument T1 is not actually done, but incorporated into the continuation as data. Thus, we get a truly tail recursive definition. This definition can be made lazy by suspending all 4 tail calls. The trampoline then transforms it into a plain loop. In the CPS version, the afterwork accumulates in the continuation parameter as data. but it seems inefficient to incorporate all the operators as well, because they are the same for every extension of the continuation. Defunctionalization is the technique to convert the continuation function to pure data and to share the operators, rather than copying them. I don't have the time to explain this in detail, but in case of function total, the relevant data consists of an integer ACK and a list data of trees, still to be processed. If argument t is a leaf, then its value is accumulated to ACK, and if data is empty, then ACK is returned. If data is not empty, the last tree in data is processed recursively in a tail call. On the other hand, if t is a fork, then the right subtree is appended to data, and the left subtree is handled recursively in a tail call. Therefore, we have obtained a traditional tail recursive definition. Its termination, however, is no longer trivial. Note that parameter data acts as a custom stack. Let's conclude the presentation. I have shown how tail recursive definitions can be turned into a loop by letting them return a function which acts as lazy, suspended value and resuming them in a generic trampoline function. The idea of a trampoline dates back to 1977. Next, I have shown how continuation passing style, CPS, can transform general recursion into tail recursion via a continuation parameter, which is a function that accumulates all the afterwork. The idea of CPS dates back to 1964 to the Mathematical Center in Amsterdam, where also Python was invented. Note that CPS does not always work. Continuations can be defunctionalized to improve efficiency. Further details can be found in my article. I hope that I have convinced you that functions are powerful computational building blocks when used cleverly. Unfortunately, many modern languages, including C++, don't support the full power of functions. Thank you for your attention.